Uh, Hello, everyone, again. We're recording this for training as one of the outputs for SUBMERSE. I'm Afonso Loureiro. I'm managing the scientific output and exploitation of the GeoLab cable in Madeira. And we are going to see today a bit of what we have found on that data and on the amount of data that is already publicly available. And for those who don't know, GeoLab is a consortium, an informal consortium that managed to bring together lots of entities to explore something that would be just a loose fiber used for engineering purposes. So there's a fiber that connects Fortaleza to Sines, Brazil to Portugal, and there's a branching unit, a branch connecting to Madeira, which has a fiber pair for communication, one TX, one RX. But during the installation, they added a third fiber just to ensure that everything was working, and that fiber is then abandoned. But they decided to turn it into something for science, and we are exploiting it. We have 57 kilometers of dark fiber, one single fiber, and we have been collecting data with an OptoDAS interrogator since 2023, usually with 500 hertz sampling rate and 10 meters gauge length. And the 3x data set corresponds to 1 week in late October 2023, and we have almost 12,000 channels, and the most important part is that we have 50% overlap between gauge lengths, and we have a sweep length of 50 microseconds. The OptoDAS is not a pulsed DAS system, it's a sweep frequency system. It allows us to go a bit further in terms of range. At Geophone, we have full resolution data available for this week, but we also have about 500 channels in mini-Cs decimated that correspond to one position at each 100 meters. The coordinates that we can provide publicly are a degraded version of the coordinates for security of the cable, and they are roughly within 200 meters of the true position. And this is a zoom to the most delicate part. And I know where the cable is, and I cannot make it the true position from these. And I know which are the good points. So if you want better coordinates than the ones that we provide, you will need to enter into a non-disclosure agreement with the cable owner. It's not even with me that you need to talk. And I'm going to stop sharing this. I'm going to move to the GeoLab, which is maybe here. No, this one. Yeah. Okay. Okay. To access this notebook, why can't I go there? To access this notebook, the address is tinyurl.com/submerse-3x. I hope that you can see it. Okay. I will write it on the board. You will need to have a Google account to log into, because otherwise you cannot connect to one of the virtual machines. Is anyone still having trouble getting to GeoLab? So the first part of this notebook, which we call it example 0, is how to access data. And for that, we will just need to run a few cells. Either do Shift Enter on each of them, or you can start running them. First part is just the installation of the necessary packages, and there will be a point where it asks you to restart the runtime, because one of the packages will need to be overwritten. You will find this happening also in other notebooks. And it's just a matter of restarting the session and rerunning it, and it will just continue. Then we will import our packages, and we are going to use Boto3 to download data directly from Geophone, from the dataset 3x. We define an endpoint, which is the S3 storage at GFZ. And then we define the resource. And the important part in this one is that we are going to use an anonymous login, so the unsigned portion. If you access any other S3 storage, you will probably need to add some access keys that will be stored in a different way. We define the bucket in this case, which is GC 3x 2023. I might make this a little larger. So this is the bucket where we'll get data. If you choose another bucket, if it's open access, you will be able to download it. If it's restricted, you will be locked out. And then we are going to define a time window of data to download. And one important part of this is that we need to add a clock offset, because at this time, the interrogator was not equipped with a GPS receiver, so it was just freewheeling at the time of the server. And we estimated it's about 2.5 minutes behind of true time. So we'll just define a time, we add a correction, and it will be easy to do. A note about the OptoDAS file naming system. They are stored in folders according to day, and then there will be either phase difference or process data, or OTDR, which is the second part of the name, and then a file which is usually 10 seconds long that has hour, minutes, and seconds. And now we're going to loop through these files, and we are downloading a few files from the server. This is just 70 seconds of data, so it's very fast to download. And now we are going to download them. So each file is about 100 megabytes and corresponds to 10 seconds of data on 11,380 channels at 500 hertz. We can check them. They're all here. And now, because we are going to need more data for a later example, we are going to define a background task to handle that download while we work on the rest. So this will just define a function. We will define a new start and end time. And we have one piece of code that's commented out so that you later can try with those times to see if there's any difference on results. And while we are doing it, it will keep downloading data. We can start to process the data that we have downloaded already. So from those files that we downloaded, we selected one at random, and we selected one channel close to shore in shallow waters, and we expect to see some signal from waves. And in this case, we see something with a period that appears to match waves. So we have something happening in the data. It's a good sign. We're not downloading blank files. We can also see that the number of samples in the x-axis scale is 5,000. This corresponds to 10 seconds at 500 hertz. So the number of samples is a match. And now we are going to get some information from the other of the file, and we can read directly what the interrogator saved on each file. So we have an HDF5 file with data header and then a data volume attached. And the important part is sampling rate, the channel length of the interrogator. We also have the gauge length and the channel spacing. In this case, it's spatial decimation. And also the unsynchronized GPS status. Just a reminder that we don't have a correct time. And now we are going to start using data. One of the things that we have here is this value, sensitivity, which is the conversion from phase rate to strain rate. If we don't say anything to the simple DAS routine, it will automatically convert from phase rates to strain rates. So whatever measures we make on this data will be already on strain rate. So that's done. And now we are going to convert this into an OpSpy stream, mostly because OpSpy has already a set of tools that are well tested, and we can use them without changing our scripts for seismology, for example. And let's just get the data. So we're going to use simple DAS. And we have the data that's arranged in the pandas data frame. So it's also easy to manipulate. Okay. We are also going to downsample it because working with 500 hertz in most cases is overkill. And in this GeoLab notebook, it will probably make us run out of memory. So I'm going to downsample it by a factor of 5. There will be also some messages tail just to indicate which is the new downsample, the new sampling factor. Okay, it's done. So these were the sampling rates from before and the new ones. This is just a very simple conversion from the DF-DAS format, the simple DAS format, into OpSpy stream. We can add more information if we need, but this is enough for most of the things. The important part, if you want to do some plotting of record sections, is that you get the distance right. So in this case, we have the dx, which is the the channel length, and we multiply it by the decimation, the spatial decimation factor. In this case, I call it Roy step because it's the name that they use on the OptoDAS software. And we can check if we have an accurate conversion. So the number of traces will match the number of traces that we saw before. The number of samples will also match. And instead of 500 Hertz, we have 100 Hertz. This is the most basic operation of handling DAS data. Getting the right files, loading them, and converting them into something useful. Next, we are going to see what we can do by processing data. We are going to do an envelope calculation. We are going to perform an Hilbert transform on the data just to highlight anything there. So we define a function, we calculate the envelope, and then we plot it. This will take a few seconds. And meanwhile, our background task is still downloading the rest of the data. Okay. So 70 seconds of data after the Hilbert transform and nice plot, we get something that looks like an hyperbolic feature and some noise. So we need to improve our image. We can apply a bandpass filter. In this case, we are going to apply it between 10 and 40 Hertz because I'm expecting some signal in that region. We have done first a spectrogram to highlight which were the frequencies. In this case, we are just going to imagine that we did that step. And we are going to repeat the envelope calculation. So a few more seconds waiting. And here I'm leveraging on the OpSpy tools. So I get the stream ST and I'm applying a filter because this is already defined in OpSpy. I point it to a data stream and it will apply all those tools that they have defined. If not, I would need to write my own code for this architecture or use some wrapper like XDAS to apply it in the same way as the OpSpy stream is now serving as a wrapper. Okay. So we have something a bit more defined, but it's still not very much different from this one. You got some more signal there. So we can take it one step further and now do an FK filter. And we are going to remove anything below 1.5 kilometers per second and then set the maximum to 99,000 kilometers per second because it's practical infinity. So anything faster than 1.4 will be preserved, the rest will be muted. And again, a few more seconds. Meanwhile, we get a message saying that the download task is finished. So while we were waiting for the envelopes to be calculated, we also downloaded 30 minutes of data. And this is a much improved version. We have not only just the hyperbolic arrival here, we have also some reflections from the seafloor and surface, and some blips here. And these are whales. So the large hyperbolic feature is a blue whale call that's being reflected, also from the sea surface and seafloor. And these blips are fin whales. And if we compare it with the other images, now that we know that they are there, we can see something here, but fin whales were invisible. Okay, this is leveraging OpSpy to do stuff. But we can also do it with raw data. The only caveat is that we need to define our own filters because we don't have a wrapper for them. So we'll just define a bandpass filter for the same frequencies, and we repeat the calculation.
Is it a speed advantage to that?
It's one less step that we have. It will take mostly the same time. But if we need to test some ideas, getting it into a stream, it's easier because we have the tools already there. Then we can adapt them. Most of the time, we just need to massage the data into the proper formats so that it behaves like a stream. Yes.
For some sci-fi and mean-high functions, if they are actually have some hidden multiple ability, so you can actually set up harmonic cores non-harmonics that are looking, which can be
yeah.
So some of them will work better on the national data.
Okay, so that's an advantage. So in this, it was actually faster than stream. So we get exactly the same result. So doing it on an OpSpy stream and doing directly on the data will get us the same result. And if you want to compare this image to the image in the data report, you will find that it is a good match. Not a perfect match because there were some parameters that were changed, but it will be the same. So we can also annotate this image, but it's just so that you can later know what it is. So we have the blue whale calls, the reflections, and then the fin whale blips. You asked that lady there because she's our whale expert. Yeah. So yeah, that will be the next example. So fin whale calls, the intercall, the time is 13 seconds, more or less. So this is what we have here. And blue whale calls will be about 50 seconds and more powerful. It's what we see here. So next, we're going to do the next example. And we are going to run a whale detector that uses a template for fin whales. And because we cannot have files in the runtime, because it's generated every time we run, we need to generate one file. We have it here compressed. We are just going to decompress it and write it. And to make sure that it's there, we can open here the Files tab, and we will see that there is a file called fin whale 100 Hertz. This is a template for fin whales that we are going to use. So we are going to reload the data set. And we are going to convert it to a stream because this detector was written around an OpSpy stream. And instead of trying to rewrite it, we'll just reuse it because we already know how to use to convert DAS to OpSpy stream. And now it's a few cells where we define parameters. The most important one is the single here that we are going to run on just one channel. We can also run in more channels and different channels. This is just a matter of running them. And now we are going to run the detector. It's quite fast for one channel. And we can see that we have the spectrogram for that channel. It's centered around the fin whale calls. And we have on each call the detection, except this one, where it detected this part here. And this is a little bit of the blue whale call that shares almost the same frequency band. But because it was stronger, it was detected. So this is a false positive. And right next to it, we have a peak, which is a false negative. So the template works, the detector works, but it's sometimes not perfect. And we can use the envelope that we calculated before and create a composite image just to show you. So the detection times list comes directly from the detector, and it will only show the results above the threshold. So we will have only these 5. This one won't be there.
So this template, I mean, it's just time domain, time series, and this is cross-correlation, or you just...
Again, I will refer to Andrea.
There's a generic call. And then you have the buffer between the classifications that we run. For example, the detector was, the template is very general, and it's triggered on the blue call. That's why I didn't detect there, because I have a specific buffer between specific detections. If I had a smaller buffer, this is just directly like
but this is similar, but it's positive.
Yeah.
No, I mean, everything that's on the
And in this case, the blue whale came at the approximate time between fin whale calls, so it was detected as something similar. And this is the interpretation with both images side by side. So the false positive is here, that small blip in the spectrogram, which corresponds to this amount of energy. And this squiggle for the fin whale is just a blip on there, and he missed it. So we can run this automatically, but we need to review it just to check if we have too many false positives and false negatives. And now we are going to forget about the whales. We are going to use those 30 minutes of data, and we are going to look at what happens near the coast. So in this cell, if we were unlucky, we would need to wait for the download to finish, but it will just immediately start loading. 30 minutes of data. This is a mistake. It should be minutes. And also because 500 hertz is lots of data, and we are going to look at waves, we are going to decimate the data into a suitable sampling rate. We could decimate it directly 500 times, but it would cause some issues. So we are going to decimate it in steps. Usually we try to get it under a factor of 10 so that it's easier. Okay. We will get information here about the new sampling rates. The first decimation will take a longer time because we are handling about 3 gigabytes of data, but the following ones will be progressively faster. So we have it at 100 hertz, and now it's just zooming through. Then we're just going to do some plotting, and this is a separation between the incoming waves and the outgoing waves, so the reflected and direct waves. And we can have the dispersion of waves close to shore. And this depends not only on the depth that we are looking at, but also with currents and the incidence angle of waves. But we can also try to plot the theoretical dispersion curve for a given depth and see if we have a match with our data. But we can also add some perturbations. So we will add a different incidence angle. Instead of just parallel to the coast, we'll have 15 degrees, and we'll have a current affecting this. So we can then plot the best case scenario with no incidence angle and no current, and we can also perturb it, and we can see that there's a skew and also something that will make these curves either a sharper V or a flatter V. Okay, and this is our first notebook. You can test this last part with a different time, going back to those uncorrected times that were commented out in the beginning. Lots of scrolling. So if you go back to these and you comment the second ones and then comment the first, you will get a different 30 minutes. It will download it, and you can recreate those figures for the wave dispersion to see if there's any difference. David, do you want to add anything?
Maybe try to stick to 30 minutes. We did a lot of tests. Obviously, you want to get, as a balance, you want to get a good amount of data in your frequency wave number plot, but hopefully you get more data for a longer
stretch, but then you get smearing effects because the sea state changes over longer times. And on top of that, and that's very important, if you get much more data, then at one point your computer will go to its knees.
So in this case, we also needed to respect the limits of disk space and memory. So that's one of the reasons that the examples used this amount of data. When you run this, you will also be able to download PNGs for the figures. So they are generated when you plot it, and then you can download them to your computer instead of having to run the whole thing again.
Maybe also with the dispersion curves, you can change the values for the current of the incidence angle just to see how it changes the dispersion curves afterwards. Like the theoretical ones, just as a test. Later on, if you want to.
That one we can do because it doesn't take that much time.
Yeah, you can go to extreme values. Just to
45. So this is with a stronger current and a different incidence angle, and the curve is completely off from what we have here in the data. We can use a grid search algorithm to find the best values. Any questions? If not, thank you.
Also to upload your own file.
Yes, it is possible. Or you can just download a notebook and point to your own data. And you run it. Yeah, you can run it in your computer because this is not very much RAM and not very much space. So
download it, the entire package.
you will come here, file, and either you download as a notebook over there, or you copy it to your Google Drive, and then you can run it in GeoLab. So the only thing that you need to ensure is that the data is, let me go to example 0. So when we download data, for OptoDAS data, it needs to respect this naming scheme for simple DAS to find the files. If not, you need to play around with it. But if the data is in a folder with the date and then DeFi and hour and 10-second files, it will find it and load it. So no problem.